Okay, so now that we all had a chance to check out the builder script and to see how quickly and easily we can actually generate a Python script with which we can run OpenMM with, let's move on to an exercise where we can play a little bit with heating and constraints and restraints and do a little bit more advanced stuff. For that, I have this little system here that I ripped out of an amyloid fibril. And as you can see, these are sort of backbone contacts between two beta sheets. And I already solvated that in waters. And I have Amber input coordinate and topology files ready for you guys in the directory. And so now that you know how to load up the Amber topology and input coordinate files, this should be a pretty straightforward thing to play with. So why don't we start with exercise. Let's just really quickly go to exercise E. If you open up exercise E, this is basically this exact same system, and it heats it up and it runs it, and it doesn't do anything beyond that. You can do that really quickly just to see that it actually works, and then in the next exercise we will change things and gently heat this system up to the temperature. And I'll introduce you guys to how exactly to do this. So if we run this through, you will see here, load the Amber topology files, and these are the file names, tetraasp, dimer, parm-top, and input coordinate file. Since I want to see things happen in the simulation, I'm setting my temperature to 600 K. Okay. Define the simulation. It's a parm-top topology. Which is followed by a geometry optimization, and then production run at 600K. And because the system is so small, you'll see a very quick turnaround, and you can look at these MD trajectories very, very quickly and readily. You don't have to wait for too long, and your laptop won't overheat. All of it will be saved in tetraasp dimer, no ions, MD without heating .pdb every 100 steps. And we have 10,000 steps total, right? So that will give us quite a bit of data to look at and see how hydrogen bonds don't exist at 600 Kelvin. So once we're done with exercise E, which really is just heating it up to high temperatures and having no heating, it's interesting to think about the concept of like, why would you want to heat something up slowly? Why don't you want to just throw it up into a high temperature and let it just wiggle around? Well, in many situations, and I've kind of learned this the hard way, you sort of have, and I can show you guys a picture of this. You have ligand protein systems, and in those cases the ligand is not covalently attached to the protein. Therefore, when you start the simulation at the very beginning, you have kind of a frustrated and a restrained system with maybe vacuum bubbles inside of the protein. And so as soon as you put water molecules in there and then apply kinetic energy, you might have a very, very fast water molecules at the very first few frames of your simulation, which could eject your ligand molecule out of the active site, and you will no longer be able to recover it until you run a very long simulation. So those kind of things can happen. And so that's why we would like to heat things up. And so the best or the most kind of like satin-gloved way to do that is to do it stepwise. And in this particular case, we do 50 Kelvin increments going from 0 Kelvin to our desired temperature. And so one way to think of that is, and particularly since we're using Python as the programming language underneath all of this, is to think of this as a for loop. So you can set the temperature And we do that right here with the variable target temperature. So we select simulation parameters. We set the target temperature to 0 Kelvin, because that's what we would like to start with. Then that is followed by a geometry optimization, and then an equilibration to 0 Kelvin. And the reason for that is because the system, the way it starts off, is always a bit frustrated. You don't really have a 0 Kelvin geometry, and so you want to remove all of the additional energy out of that system to get really down to the bottom of that local potential that you might be in. So let's do that for exercise F. Let's step through each one of these steps. We load up the same exact parm top and input coordinate file with the ASP tetra. We set the target temperature to 0 Kelvin. We do geometry optimization, which is done now, and then we do an equilibration run. And to give you a really quick example of what this equilibration run actually looks like, and you can see how I'm removing energy out of the system, how it goes, every step, every increment has less of a geometric change if you look at it. So that's basically what we did just now. We just removed, we froze the system to 0 Kelvin. Okay, so the next step is that of a heating. And remember, we set our variable of the simulation temperature right here, the target temperature, we set it to 0 Kelvin. Well, that's a variable, and you can populate that variable with new values. So you can populate it with 50 Kelvin and then run a simulation at 50 Kelvin, and then you can do the same thing for 100 Kelvin and so forth. But because we're lazy, we don't want to do that all the time for like all these steps, so we write a for loop. And in that for loop, we say, for this variable, in the range of 0 to some number by some increment, we assign that temperature to our integrator. And then we do a set of simulation steps. Now, your task will be to figure out what exactly to put in here to make it actually physically relevant. Because we want to go to 300 Kelvin in 50 Kelvin increments. And right now what we're doing is we're going from 0 to 10 Kelvin in 2 Kelvin increments. So remember, our current temperature is 0, our target temperature is 300, and our step size is 50. To 300 Kelvin required you to type not 0 to 300, but 0 to 301, or maybe 350, or anything in between that. Because the last number in this for loop is not actually going to be recognized, so you have to type a number that's larger than your target number. You could have also gone from 50 to 301, because you already were at 0 Kelvin after the equilibration. So the first step went straight up to 50. A couple of you have asked me why it's even important to heat in the first place. Well, for a silly system like this, it doesn't really matter, because it's not interesting. But for a drug design type of a problem, when you don't have infinite resources and you don't have the luxury to have a ligand that's free in solution and a protein that's also by itself free in solution to meet at some point by randomness, you typically start off with these MD simulations from a best case scenario in which you assume that that ligand already found its way into the active site. Well, because you want to take, you analyze as much of your data as possible, you would like your data to equilibrate as soon as possible, and therefore you would like to initiate all of that potential and kinetic energy into the system in as gentle of a fashion as possible, and that's where the gentle 6-step or even more step or lower step heating, but stepwise for sure, comes in really handy, and you guys will then at least have a good starting geometry at good, like without any artifacts, without any hotspots in terms of temperature that are maybe unevenly distributed across a system and might cause artifacts which you then will not recover from until you run a lot of sampling. Okay. All right, so we're pretty much coming to the end of this, and I just wanted to show a couple of really quick things. We don't really have time to go into detail. Two of the other things on the item list were constraints and restraints. And you guys can definitely look at those scripts. They are script G and H. G is heating up with constraints, and if we look at that script, it basically adds constraints with this particular line right here. And what you do there is basically you specify the add constraint part of the system object, and you say which atoms, atom 15 and atom 18, you would like to add a constraint to. And in this particular case, I simply set it to 1.8 angstroms. What this basically does is it freezes the distance between those two atoms at exactly that distance, and it won't allow it to move closer or farther apart. So basically what you do with that is you force the surrounding system to accommodate this constraint. So it's a very unphysical thing. It's very quick in terms of the turnaround and in terms of the computational effort that goes into this, but it's very non-physical. It's something that you might want to do to check out a few things, or to maybe move a ligand closer to a place or farther away from a place and see what happens to the surrounding system. A much better way to do that, a much more physical way, is to apply restraints. So that's this exercise H. And all of these are the same system. So this is this silly tetra-aspartate dimer. But the biggest difference here is this portion where you add restraints. So now you don't only specify the atoms that you're interested in, and you can find out what atoms these are by opening up the PDB file in VMD and then selecting the atom. These are the scripts H and G, and it will be really educational if you guys want to check this out as a homework assignment for tonight, and then come back tomorrow with loads of questions. I hope you guys had a little bit of an aha moment with this. I did when I prepared these slides, for sure. Thanks.